Okay, in this video, we're going to consider a different type of spaghetti rates problem. Let's say that this is a ground surface here, and above the ground there's a giant balloon, and the balloon is rising upward at a rate of 15 feet per second. And along this surface there's a car, and when the car is directly underneath the balloon, just at that moment the balloon is 200 feet above the ground, and the car is moving this way at a speed of 45 miles per hour, or that would be 66 feet per second. So the balloon is 200 feet off the ground. It's rising at the rate of 15 feet a second. Just when the balloon is 200 feet off the ground, there's a car directly beneath it, and the car is moving to the right at a speed of 66 feet per second. The problem is this: 1 second later, how fast is the distance between the balloon and the car changing? Now, we are given the rate of rise of the balloon, and we're given the speed of the car. The balloon is going straight up. The car is going straight to the right, so we can draw it something like this. We can call this the y direction for the balloon, and we can call it the x direction for the car. And we know it says that the balloon is rising at 15 feet per second. So we know what dy dt is. dy dt equals 15. And we know what dx dt is. That's 66. What we're asked to solve for is, here, this is the balloon here, here's the car. We're asked to solve for what is the rate of change of the distance between the balloon and the car. And this we just call h. So we want to find dh dt. At a moment it says 1 second later, so the car is directly beneath the balloon. The balloon is 200 feet above the ground and rising this fast. The car is going to the right 66 feet per second. And now it says 1 second later, with this distance here will be 66 feet. 1 second later, this distance here will be 215 feet. It was 200 feet. When the car went over here 1 second later, the balloon went up 15 feet. So this is 215. So what the problem is asking us is, if we know what dy dt is, we know what dx dt is, we know what x is, it's 66 feet, we know what y is, it's 215 feet. Okay, when x has this value and y has this value, what is dh dt? That's what we have to solve for. So we look at this and we realize, well, it's not too difficult to find a general equation that relates x and y and h. That's just going to be h squared equals x squared plus y squared. Now we're given what dx dt is and dy dt. We have to solve for dh dt when x equals 66 and y equals 215. Okay, before we do that, let's take derivatives then. Here we're going to have q times h dh dt and that will equal 2 times x times dx dt plus 2 times y times dy dt. Now it looks like these 2's here are going to cancel, so we'll get rid of those. Now, we know what this is. Put one erase or a minus sign. We know what dy dt is. We'll want to solve for h when x equals 66 and y equals 215. So we can solve for h using this. So we know what h is. Now we can solve for dh dt. That's the only unknown there. That's what we're asked to solve for. So first, let's see. If x is this and y is this, h will equal the square root of 66 squared plus 215 squared, and that comes out to equal just not quite 225 feet. It's 224.9. So we go back to here, 224.9 times dh dt will equal x. X is 66 times dx dt at 66 feet per second plus y. Y is 215 times dy dt. That's 15. So dh dt that will be equal to 66 squared comes out to 4356 plus 215 times 15 is 3225. And we want to divide it by this, 224.9, and that's approximately equal to 37 or 33.7 feet per second. And that's the solution. So let's just take it from the beginning again. The way the problem was set up, stating that the balloon is 200 feet off the ground, there's a car directly beneath it. We know what the car is traveling at, 66 feet per second. We know how fast the balloon is rising, 215 feet per second. So 1 second later, we know what this distance is. That's just 66. And we know what this distance is. That's going to be 200 plus 15. 215. So we know what x is, and we know what y is 1 second later. The distance between them, that's h. Obviously, we can solve for h. We did that here. Okay. Now, we want to know what dy dt is, and we know what dx dt is. What we're asked to solve for is, what is dh dt, and the problem said 1 second later, so that means we want to solve for dh dt when x equals 66 and y equals 215. Those are the values it's going to have 1 second after the car was directly beneath the balloon. So we need some equation that relates x and y and h. And of course, that's real obvious. That's going to be the Pythagorean theorem. So h squared equals x squared plus y squared. Now we take our derivatives. H dh dt equals, there's 2's here, we cancel those out. X dx dt plus y dy dt. We know this, we know this, we know this, this is given, this is given. We can figure that out from this. We can now solve for our unknown. So again, it's like the very first problem is that you want to write down what is given to you. Here's the rate of change of the variable that you're supposed to solve for, and here is an equation that relates all the variables together. And then once you do that, you're set up to take your derivatives, and once you do that, with the remaining information that's in the problem, you're all set up to solve for dh dt. And that's it. Hope it was worthwhile, hope it was helpful. Come back, we'll tackle another one of these types of problems here where the relation between the variables is not just a simple Pythagorean type relationship.